So thanks, Filip, for bringing me here. It's a very, very, very great pleasure to be at this centennial conference. And furthermore, it's even more pleasure to be probably the youngest speaker of this conference. So thank you very much. I think so. Okay, so today I'm going to talk about Floer-theory. So that will be about symplectic topology, which I think most of you guys don't really deal with. So I'll try to be very polite, very definitions, and very brief with any technicalities, so that this would be something we can follow. Okay, so it's a joint work with Alex Ritter, my ex-supervisor, and what we do here is we use Floer-theory, Hamiltonian Floer-theory, on certain manifolds which have C directions. So such manifolds arise a lot from representation theory, like in invariants or symplectic resolutions, but also they arise from other algebraic geometry like Higgs bundle moduli spaces, which we're going to see in the end, and also like toric varieties. So basically, whenever you have like a manifold or just symplectic with a C direction, which has some nice properties, then you get this interesting filtration on the ordinary cohomology of the manifold using Floer-theory. Okay, so I guess in the first slide, I will just say the gist of what's going to happen at the top. So we start with a symplectic manifold with a C direction, which is pseudo-holomorphic. When I say pseudo-holomorphic, I mean whenever you have a symplectic manifold, you always have this almost complex structure which is compatible. That's the first thing which one learns in symplectic topology. And then using this almost complex structure, if you have a C direction which is compatible, then that's the setup which we start with. And the S1 part of the action is Hamiltonian, which means the flow of the S1 action not only preserves symplectic form, but it's also there's a Hamiltonian, so that these are Hamiltonian. Okay, that's the setup. And then what we get out of Floer-theory is so we first consider Floer cohomology of the S1 moment map of this. So we have S1 being Hamiltonian, it means there's a function H, so that its Hamiltonian vector field is the S1 action. So we use this Hamiltonian, and also it's multiplies to get our this structure, this filtration on the quantum cohomology a priori, which is not so weird because quantum cohomology and Floer cohomology they're connected. The quantum cohomology is somehow Floer cohomology for a small Hamiltonian if the manifold is open. Now I didn't say in this slide, but our symplectic manifold is always assumed to be open. Otherwise, the story is just trivial. It doesn't make sense. We'll see that in the next slide. So the outcome, you get some interesting, some curious filtration, some invariant of this symplectic manifold together with the C direction. So different choices of this C direction phi are going to give you different filtrations. So that's interesting thing to consider. And then furthermore, if you don't like quantum cohomology, you prefer to be algebraic topologist or something, then you can just remove the Novikov parameter, which happens in cohomology, just specialize in the base field. So you get filtration on the ordinary cohomology by coupling it. That's an interesting invariant of your symplectic manifold with this interaction. So that's the gist. Now, of course, the problem in Floer-theory is always about the computations. So we can define things, but then how do you compute things in Floer-theory? Though you have to count some pseudo-holomorphic cylinders, and who is going to do that really? So similar like quantum cohomology. So the point is, it's always a problem how to explicitly compute this stuff. We will see in the next slides like some partial information, so we can compute this part or that part. But in general, what we do is we use spectral sequences in order to compute this filtration. And that's going to be the second half of the talk. How do we get to them? And some easy examples. So in the end, what is interesting, okay, we've got some invariant from your Floer-theory. The interesting question is how does this invariant compares to any invariant you have in real life or in mathematics? So in particular for Higgs moduli spaces, there's this reverse filtration, for example, and then maybe a good question is how do you compare these two? Are they comparable at all, or what's the difference? How big is it? Okay, we'll see that in the very last slide. Okay, but then getting to the Floer-theory, let's just in one slide, let's just go through the usual definition there so that we're on the same page. So Floer-theory, what it does really, it studies Hamiltonian flows. So like in Riemannian geometry, you have the gradient flow, right? So the vector field, which is dual to the differential function, That's the same thing as Hamiltonian vector field in symplectic topology. And that's what we start with in Floer theory. So what Floer observed, famously in his papers in late 80s, he observed that you can construct a chain complex out of a Hamiltonian flow. So basically all the data comes from this vector field, which you get from your symplectic form and the function. So first, the generators of this Floer chain complex are the one periodic orbits. You can see this solutions of this OD, so one periodic orbits of the Hamiltonian flow, and that's the generators. But then the differential counts some pseudo-holomorphic cylinders. So we have two periodic orbits, and then we have this U satisfying this elliptic PD. So it's like a Cauchy-Riemann equation, but then perturbed by the Hamiltonian vector field X stage. So that's why they're called perturbed pseudo-holomorphic cylinders. Pseudo comes from the fact that this I doesn't have to be integrable holomorphic structure; it can just be almost holomorphic structure, which, as we said, always exists in symplectic. First thing we learned. Okay, so then the upshot, and the striking upshot in the early days of Floer-theory, and why this was important. Floer wanted to prove this Arnold conjectures. Now, Arnold conjecture said that this number of this one periodic orbits, which generate this Floer chain complex, is at least the Betti numbers of the space. And then the point is, so Floer proved that the homology of this chain complex recovers the ordinary homology, which then means that the rank of it is definitely smaller or equal than the rank of the generators, which then proves the Arnold conjecture. So that was the kind of the outcome of Floer-theory for closed symplectic manifolds, torus, things like that. But that's exactly not what we're doing today. So today, in order for this story to make sense, we need like an open symplectic manifold, and then this story becomes questionable. So what is Floer cohomology of arbitrary Hamiltonian for open symplectic manifold? The answer is we don't even know whether it's well defined. And the problem which occurs is, so let's say this is it's a open symplectic manifold. We have two periodic orbits. Then who says that I don't have a sequence of these cylinders which go to infinity? So a priori, we don't know that. And that's an analytic problem compared to the closed setup where you don't have it. So all these, there's some Gromov compactness story which works really close. When you're open, not a priori. So you need to deal with that. So
why is that bad?
Well, it just, we count things. We want a finite number, right? So in the differential, we want the x is y times the number of these guys.
Oh, we're counting that.
Yeah. So I guess these count.
Okay.
Yeah. So just a priori, we want to exclude having infinite many of these. So you need some nice infinity. So like not only there's different type, but there's symplectic. We'll see in the slide. So the upshot is if you're open and then this Hamiltonian H is like C too small, so like small enough, then again the Floer cohomology recovers the order. But that's a simple thing. It's like just analysis tells you that if your Hamiltonian is small, then really you don't get these one periodic orbits. They don't get too close, so you just get Morse-theory basically, and these U's are just gradient trajectories. So then the Floer cohomology is just Morse homology, and that's your. So that's simple. But the problem occurs is what if you want big Hamiltonians, and what is then HF, and why, what happens in infinity, and so that, as I said, the issue is non-compactness. So the usual way, so the way people did it.
Is there an index associated that differs by one?
Yeah, there's that as well. There's grading. I don't go to details, but yeah, there's only that index, which something about symplectic flow when you go around, and then the symplectic matrices. There's a kind of winding number if there's unity. Yeah, indeed, there's not. Yeah. So fortunately, there's a lot of details. If I start explaining, well, we will not finish before Nikita. So okay. So the usual way we deal with the non-compact symplectic manifold is we assume this legal condition, which is that my manifold is open, but apart from a compact set, it's like a cylinder. So it's some sigma times 1 plus infinity. So it's a cylinder, like half cylinder if you like, but the symplectic form here is exactly this B R alpha, where alpha is a compact form on this necessarily compact hyperspace. So that's And I guess historically the only way people deal with the open symplectic manifold, saying that you assume this kind of harsh condition of infinity, symplectic condition, and then you can deal with this non-compactness. So these things, they don't appear. And there's a reason why. But then you also choose Hamiltonians, these h lambda, which is lambda r, and r is this coordinate here. So you use Hamiltonians, which are linear with respect to the radial coordinate, so that things will work out, so that you don't get these infinitely many cylinders. Reason for that is that if you have such setup, so yeah, that's before that to say, if you have such setup, then what's going to happen is first these periodic orbits are going to lie on like r equal to constant slices, and also the radial coordinate of these Floer cylinders is going to satisfy maximum principle. So when you transfer Floer equation for these very special Hamiltonians, which are linear with respect to radial coordinate, then it looks like this PD, which satisfies the maximum principle, like the r coordinate. And then what it means is like you can kind of go down, but you definitely cannot go up more than the maximum, whatever is the maximum of those radial coordinates of these. So that's the outcome. That's something like 20 years old. This is like historically very important. And so that's what we can do for open symplectic manifold, which is of this type, so the Liouville. So by the way, somebody heard like Stein manifolds are Liouville. So if you're an algebraic geometer, Stein implies Liouville. So, but not the other way around. There's Liouville, which is not Stein, but just want to focus on things coming from algebraic geometry. These are all Liouville, so they give you a lot of examples of this type. So the upshot is that we want invariant for this symplectic manifold. And then which Hamiltonian I want to choose? Well, let's choose these Hamiltonians, which are linear, this lambda r, and then these four cohomologies are well defined because of this maximum principle. But also I can make a maps between them, which are called continuation maps. So HF of H lambda 1 can go to HF the H lambda 2 by the same kind of Floer type equation. So same PDE, just the difference is that this XH is going to have XHS. So the Hamiltonian is going to interpolate between the smaller and the bigger slope. So those are similar equation as this one. And what's also true is that this equation of this continuation map also satisfies the same maximum principle, which means it's well defined. So the outcome is that you get this invariant called symplectic cohomology, which is obtained using these Floer cohomologies and these directed system of continuation maps. So you start with a small slope, get to the bigger slope is this lambda, right? So the linearity constant. So you go to the bigger one, and so once you get a directed system, you just define the direct limit to be the symplectic. So that's for many reasons, that's a natural invariant to look at for this open symplectic manifold. The motivation for this comes from many different reasons. One of them is like looking at this contact manifold, and then if you ask people in contact topology, they wonder, are there any red periods? So there's some red vector field in this contact manifold, and then the answer is if this symplectic homology is 0, it means that some period had to kill the Morse part here in this direct limit, so then there is a red orbit. So that's one outcome. Like this symplectic invariant distinguishes whether you have some red orbits on your. That's one thing. The other one is, do you have exact Lagrangians in the symplectic manifold? Well, again, if symplectic homology is 0, then there are no exact Lagrangians. That's a theorem I cannot explain now, but somehow we realize that knowing information about symplectic homology can give you something about your symplectic manifold. So it's interesting invariant. And furthermore, to just see that it's not some silly ring, you get, for example, for a cotangent bundle being like the canonical phase space, the simplest open symplectic manifold for a cotangent bundle of a compact Q, this recovers the homology full space. So together with the product, here in a symplectic homology, the product is going to be this pair of pairs product. So pair of pairs product does something like counts these things. So that's a product. In SH, for the cotangent bundle, it recovers the Chas-Sullivan loop product on a low space of Q. So that's Peter-wise, it's a very important result. So, all in all, the story is that for open symplectic manifold, this symplectic homology is something you want to look at, and it can be something interesting and infinite dimensional. It can be infinite dimensional with a difference from the closed case where it's just the ordinary homology. So, fine. Okay. So then let's look at this C to the n. Before getting to, so our story works for any symplectic manifold with a C direction where we construct the symplectic homology. But let's look at C to the n being like the most trivial example, and let's understand what happens there. So C to the n has a natural C direction, just a scaling relation, and the moment map this of the S1 part of the action is just basically the distance from the origin square. Okay. Now observation 1 says, okay, well C to the n is very simple, so everything somehow collapses to be the same thing. By saying that, I mean, well, first it's lineal. So the lineal structure of C to the n is simple. You have this compact hypersurface being your sphere, and then the distance is your radial coordinate. So, well, the distance squared, right? So, so what collapses there is that the S1 moment map of the C direction of the S1 action is actually the same thing as the radial coordinate. So as an outcome, we've seen the story for linear manifolds that we can construct this symplectic homology using the Hamiltonians, which are linear with respect to the radial coordinate. But for C to the n, the radial coordinate is same as S1 moment map. So we can just simply say, okay, well, let's forget about the radial coordinates and let's look at the moment map being my Hamiltonian, my canonical Hamiltonian fuse here. Okay, so this is just rewriting from the previous slide saying, okay, well, SH is then the limit, the direct limit of these Hamiltonians, which are linear with respect to the S1 moment. Why I'm switching from radial coordinate, because for more general setup, I don't have radial coordinate anymore. I'm not going to be a zero. So then I just have this moment map, which is going to mimic radial. That's why I'm asserting this equality here in this point. Okay, so that's this being real. And the second observation for C, which works for C to the n. So unlike the loop space, something compact. Sorry, unlike cotangent bundle, something compact. C to the n is cotangent bundle of R to the n. So this story with loop space doesn't really work. So you get SH is actually 0. And why? So what's how to prove that SH is 0 for C to the n? It's exactly what Dennis asked. What is the grading here? So the grading here, and why you can compute the grading. So in general, computing grading these indices, these points is horrible. You just don't do it like anything else in Floer-theory. But here, the grading can be computed basically because it comes from a holomorphic cis direction. So the flow is holomorphic, and then, as I said, the grading for holomorphic things become basically binding number of unitary matrices. So how do you get this 2n floor of lambda? Is basically just saying, lambda. So H is S1 rotation. So how much S1 rotates the canonical bundle of C to the n? That's one thing. And then lambda H is basically this floor of lambda, floor function of lambda times rotation. So that many rotations of canonical bundle. And then you ask yourself, okay, well, you do those rotations, and what's the binding number of these unitary matrices? So that's what's going to give you this 2n floor of lambda. So basically, that's the gist. And somehow the point is, and that's how you get the grading, but the point is that there's a lot of flexibility in Floer-theory. So doing this floor homology, HF, I said take Hamiltonian, which is linear with respect to the moment map, but it doesn't have to be exactly lambda H. So my Hamiltonian can be, so H lambda is equal lambda H at infinity. But for C to the n, things are simple. You can just take lambda H to your Hamiltonian. That Hamiltonian is where, if lambda is irrational, so it doesn't close up, the floor chain complex for this Hamiltonian is very simple. It just has the origin, because everything else doesn't close up in the integer time. So that the origin is, that's this 0, that's the only generator of this floor chain. And the grading comes from this, how much do you line the canonical bundle? Now, the story with canonical bound is important that the first term class is 0, which then tells you, okay, canonical bound is trivial. So then the trivialization is computing this. You need to go to the local chart. Okay, so that's the proof. And okay, another part is that this continuation maps, this direct limit, they preserve the grading. So then, if the grading for small lambda, right, for small lambda, well, let me just look at this formula. For small lambda, this grading is just 0, so that's the Morse grading. But then, as soon as lambda gets like 1 plus something, the grading gets minus 20. This is a cohomological grading notation, so it's minus. And then for bigger lambda, you get minus 4 and so on. So already in the first step in this direct limit, you lose your generator. So direct limit is 0. So that's the argument for why SH is 0. So this is like a kind of grading argument, but the outcome of this, for example, is what Gromov showed in this 1985 seminal paper, which is that there are no exact Lagrangians in C to the n. Because I said, like, if SH is 0, there's argument which says then there's no exact Lagrangians, which Gromov proved. This was before spectral cohomology, but that's an important fact here. And also, SH being 0 tells you that, of course, there are Reb orbits in S2n minus 1, but there are also Reb orbits on any hypersurface of convex type, somehow like of convex type, for the reason that we can think of C to the n being a completion of that. So you get this Weinstein conjecture solved for all the those in C to the n just because knowing that SH is 0. So, okay, this is all about C to the n, so we're going to get further, but just wanted to explain what happens to C to the n, because C to the n is very simple. The third observation, it's important, is that you can get a spectral sequence. I mentioned in the first slide. But how do you get spectral sequence? Well, guessing cohomological algebra, if you get some filtration of a gradient complex, then that gives you, as a consequence, spectral sequence. Now, which filtration I want to use? Well, in the Keita talk, he mentioned the action filtration. So it's this PDQ integration minus integration of H. So that's this AH lambda. So whenever you're linear, so you're exact, so you have this PDQ form, so primitive form, you have the filtration by that action function. Because Floer-theory is Morse-theory of the action function, which means you go along the cylinder, so the value of the action function is going to get reduced. So that gives you the natural filtration on your chain complex. You know, along the differential, you get reduced. The value of the action function is just getting smaller. So, but furthermore, this filtration actually follows the value of H, which goes, so the point is your filtration of your chain complex is going away from the origin, you're getting filtered more and more, going to the next level of filtration. But what's the chain complex here? The chain complex is not the simple one we had, lambda H, in the, so here, right, to prove that SH is 0, I use very stupid, like just lambda H Hamiltonian, which is just linear, and that's it. Whereas here, I want to use Hamiltonian, which is convex. So it actually collects some interesting orbits. So how that looks like? Yes. There, so this lambda H Hamiltonian is just linear, and the only orbit here is just the origin, right? That's what we had in the previous slide. Here, I want to use Hamiltonian, which is more interesting. So it starts from being 0, and the slope increases, and eventually it converges to lambda H. So this is irrational slope. But what happened is on the way, we're going to get some orbits. And the orbits are exactly going to happen when the slope is integer. So slope 1, slope 2, slope 3. What are they going to be? They're going to be exactly the red, or the S1 action, or so like the whole sphere. So on the period 1, you're going to have the whole sphere S2n minus 1 of red periods. When the slope gets to 2, you're going to have also sphere, but basically double orbits. So they're the same thing, but you just go along the 2 period, and then 3 period, and so on. So in particular for C, you're just going to have like S1, then S1 twice, S1 three times, and so on. Okay, so that's, and then as I said, this action function is actually going to be, the value of it is going to be where does the tangent line intersects the y-axis, which then tells you, you know, like as you're going further away from the origin, your filtration is getting less and less. So that's exactly how the complex gets filtered. So as I said, as I promised, the outcome is, you know, you have a filtered complex and it's a gradient. So that's how you get one and the other gradient for the spectral sequence, which then should converge to your Floer cohomology. But then if you continue doing this, so if you continue doing this for bigger and bigger lambdas, you can actually get to the whole symplectic homology complex, which then gives you filtration, the spectral sequence which converges to symplectic homology. Okay, so what this is the example for T, just not one-dimensional simplest example, and then these spheres I have here are just S1s, right? So here what you're seeing in the columns are, the first S1 is that like one periodic thing. The second S1 is two periodic, and like period two, and the third S1. You just go further and further. How do you know the differentials? Well, then we connect to the previous slide, because previously we proved that SH is zero. So if this spectral sequence has to converge to SH and SH is zero, it means that everything somehow has to vanish. So everything has to delete each other. And the way we present usually the story, the grading, is not PQ, but P plus Q slash P. P plus Q is the cohomology, the total grading. So then what I'm saying is the differentials, they have to go one row up. So if you have this picture and they have to go one row up, this is the only way the things can cancel each other. So that's the consequence you get. And then of course the not column is just the Morse part. So that's the origin here. That's why you just get. Yes.
Can I think of this filtration as can do the fact that the action has two terms? One is related to the rotation of the loop, and another is due to the Newtonian.
This.
Right. So the first term generates rotation of the loop, and the second is both the actual loop motion. Symplectic space, so you can filter by first and by second term separately.
I mean, like filter by this and by that versus the. I mean, doing that is going to give you like these two indices. All right. Yeah, I'll think about it. I don't. Sure. In what? Yeah, I'll think about it. Maybe. Yeah. That sounds possible. Okay, so then I'm showing this basically because this is like a basic example of space we do. So C to the n is like the trivial, topologically trivial symplectic manifold with a C direction. But then of course this is old story, this is nothing new. So the whole question is, okay, what do we want to do now? Let's think about anything beyond C to the n, which has the C direction. Can you go and do the same story? First problem, of course, goes back to the picture which was here, which if you remember, I said you have an open symplectic manifold and you have some Hamiltonian, and why doesn't go to, why we don't have these cylinders which go to infinity, like how to tame this, how to get this maximum principle here, which we had for Liouville. So C to the n is Liouville, but it's basically the only Liouville, or almost the only Liouville manifold with this direction. So that's exactly when the old story breaks. So you need to deal with this non-compactness. So that's the kind of the technicality part. And then when you get to that, and we can redo all the story, like spectral sequence and everything, what to do with that, like what's interesting. And that's when we come to this filtration, which I mentioned, which is the main invariant. Okay, so let's think about how much we can extend this C to the end. So what are the good conditions for multiplicity? Then we get to this definition of symplectic system manifold. I guess the name already says so. It's symplectic and it has a C direction. And the way you want to think about it is, well, first what we happen to need is that it has the C direction, which is pseudo-holomorphic, so compatible with the almost complete structure, and the S1 part is Hamiltonian. Why we need this? Well, because remember this radial coordinate here for C to the n was the same as this moment map. So we don't have radial coordinate anymore, but moment map we have. That's going to be our radial coordinate for this like a quasi-real story. Okay, so that's definitely must do. Then you think about the arguments for C to the n, the fixed focus of the C direction generators. You realize that you need some kind of compactness condition for the action. So the whole space is non-compact, but if the action is contracting, meaning that the C direction, when you do the flow, t goes to 0, it go to a compact submanifold, then you're fine. So that's kind of geometrically retained, not symplectically, but geometrically. So that's this first condition, which says, okay, the fixed focus is compact, and every point has the limit of, like, if you look at the theta orbit, it has a limit when t goes to 0. The other limit, of course, doesn't have to exist, and that's how they find the core. So core, if you think about the Liouville manifolds, would be something like a skeleton, like a little, like a Weinstein skeleton, a little skeleton. If you thought about the C direction being Liouville vector field, which you see to the end is the same thing. So it's just a radial vector. Okay, so then, okay, kind of mimicking what was previously known, we have kind of geometric theorem here, which recovers some results which were known from about the compact case. So what's happening is this core, distinguished mimics the skeleton, is compact, and it's a deformation of Ritter to the whole space if things are nice, meaning that you have a CW pair, which again always happens if you're an algebraic geometer. So if it's a variety, it's always true. And then the cohomology localizes to the fixed focus. So we want this fixed focus to be compact. In general, it's going to be a couple of connected components, and they recover the cohomology of total space. So that I'm saying that's like it's a small story by Tia Bott, but we're just proving that it works here for this non-compact, slightly weird setup. Okay, and then yeah, as a consequence, there's only one minimum of the moment map because of the Betti numbers in the left hand here. We assume that these are connected. Okay, so that's kind of just about geometric setup, which we have, and some structural theorem. Now, now the real thing is this enough? Is this enough to exclude the possibility of these cylinders going to infinity? So that's a real question, and the answer is I don't know. We tried to get this sort of maximum principle using just these conditions, but it's not really, you just a priori cannot get it so easily because maximum principle for Liouville manifolds, you really use the primitive one form, and in every step of the proof you really need it. So we realized we need something more, and yeah. So this is why it's rarely exactly infinity, which means it doesn't have a primitive one form. That's a problem for the maximum principles work out. Now, what happened is actually, as I mentioned before I said this, as I mentioned, we worked with these pre-varieties, these symplectic resolutions, and they actually satisfy much more than what's written on the previous slide. So yes, you have a C direction, it's very nice, but actually it has this resolution now, right? So what is a symplectic resolution? It's continuing to what Nikita mentioned, symplectic singularities are there. So symplectic resolution is the projective resolution of symplectic singularity. So projective means proper as well, proper topologically, which means that the inverse of a compact is compact, and also it's compatible with a lot of stuff. So okay, so this is the kind of the condition which we had, which comes naturally for this symplectic resolution. So it's extending to many more other examples. So what we want here is to say, okay, apart from a compact, there's a proper map to this, to the end of the Liouville manifold. And why that is good? Because for the end of the Liouville manifold, we know that it satisfies maximum principle. Things are tamed here. And if you're proper above something where things are tamed, then you do the pullback, and then whatever you had upstairs is going to also live in the compact, so nothing goes.
What is I? Capital I.
Yeah, so that's an almost complex structure, which we fix at the top. So the one with respect to which action is homomorphic. So it always choose like symplectic manifold, choose almost complex structures compatible, and the action is isomorphic. So yeah, saying this in one line says I goes to IB. What is IB? It's something I didn't mention here, but it's important. So IB is just like a almost complex structure here, which is compatible with this convex structure in a way that alpha is ER circ IB like this. So this is what we call contact almost complex structure of quantum time. That's important to get as maximum principle. So basically what I'm saying here is all the data here upstairs is compatible with the nice data downstairs. That nice data which gives you maximum principle. And then if you have it here, then also the Floer solution upstairs is going to project to something like a Floer solution downstairs, which infinity is Floer, since that's a maximum principle. So in background, long story short, is the analysis works. And then just the name of this, we coined the symplectic system manifold over a convex base because this is what we usually say symplectically convex. So, okay, altogether, this reasoning tells us that for these manifolds, the story that we get for theta d n actually works. So you can define these Floer cohomologies. And the main examples of this, this feature which kind of looks weird, there's actually a lot of examples. They don't need to be necessarily resolutions. We started with resolutions, but you can have any proper morphism, because any proper morphism will do this to any affine variety. Because how do you get from affine to Liouville? Well, affine variety is something in C to the n, and C to the n is Liouville. So the point is, as long as you have a projecting morphism to affine, which has a contracting sister action, you can embed that to C to the n with a contracting sister action, and that sister action is exactly going to be the nice one which we use for C to the n. So this gives not only these symplectic resolutions, but also Higgs moduli spaces because there's a Hitchin map, and also same projecting toric varieties. So for people who like toric variety, the same projector just means it's like a GT quotient. So for me, that's any toric variety, but depends who you ask. It's not true. Okay, so in general, you get a lot of interesting examples coming from algebraic geometry, which satisfy this criteria. So for any of this example, I'm having a sister action, you get that this Floer cohomology can be defined, and furthermore, this is like so the upshot of this is this theorem, where I just rephrase what I said. Right, so that whenever you have set up from the previous slide, these Floer cohomologies can be well defined because of the maximum principle which works. Floer cohomologies of Hamiltonians which are linear with respect to moment map. So I told you in C to the n, you had a moment map which was the same as radial coordinate. Now there's no more radial coordinate, it's not legal. Then you have a moment map by definition or by assumption. And then you can get this invariant, symplectic homology. Moreover, what's interesting is whenever you are in this algebraic geometry setup that your morphism above defined, then this symplectic homology doesn't depend on the choice of sister action. That's interesting. So, for example, for historic varieties, you have a whole torus acting. So you can take one parameter sub-toruses, and they're all going to give you the same invariant. Which actually, for toric varieties, that's anyone who's interested, the symplectic homology is going to recover Jacobian of the superpotential. So toric variety has this Delzan polytope. From Delzan polytope, we can get the superpotential. It's a harmonic function, and this Jacobian ring is you do differentials on this polynomial, and you can construct it. So this invariant, the symplectic homology we get actually recovers this Jacobian. So it's
like a mirror symmetry.
Looks like, yeah, looks like. I would. Yeah, talk about it later. The problem is this symplectic structure is very weird. It's not the one which usually appears in mirror symmetry. Like it's not legal, it's horrible. So, but it's interesting that you need to recover something. So maybe there's some hidden mirror symmetry there, but I cannot understand. Okay.
I'm worried about the statement because you have isomorphism.
Yes. That's addition, yes.
Huh?
That's what I said, it's addition. It's an interesting statement. That not only we get this invariant, but if the setup is that you have more actions, then you get isomorphism between these two different symplectic modes.
When you say why X is a morphism, which gives you the action for some isomorphic. Right. Just a morphism.
No, yeah. So sorry. So the map. So see the map is morphism. So this refers to the previous slide. So previous slide I said what are the nice examples are these algebraic morphisms. I'm saying in that setup, where you have not only one cis direction, but maybe two or even more, then the symplectic homology which you get doesn't depend on the choice of the action. Because basically x you get in C to the n, these cis directions just appear as like positive linear combinations of the coordinates, kind of sum. This Hamiltonians are going to be like sum of ni zi squared. And the point is, you can always majorize this one with the other one with some bigger lambda, so you can kind of make this combination out to go zigzag. And then, because SH is going to be the direct limit of these things with different slopes. So somehow the contracting condition tells you that these are all positive. You can always make bigger combination, bigger and bigger. That's why isomorphism is true. So I can explain that in detail if you're interested. But saying whenever you have a morphism, this is isomorphism between the SH, not psi being isomorphism.
It's just that, isomorphism of homology is sort of like homotopy equivalence or strong motion equivalence. But you just have a morphism between two equivariant structures.
It doesn't say that homology X. Why?
Yeah, it's yeah.
Okay.
Yeah, that's what I'm saying.
Okay.
This big morphism, this big, it's yeah.
I can't read. Okay.
Sure.
Okay.
I thought this was big.
Doesn't make sense.
Okay, sure. So that's the observation one. We can do this in like homology for these manifolds. That's great. The other thing is, remember for C to the n, we had this grading argument that the symplectic homology of C to the n was 0. So the same works here again, as long as you have Z grading, which is, remember we talked about canonical bundle and its trivialization. So we need Filtrations class to be 0, trivialized canonical model. And then similar argument, now technically more complicated. I'm just thinking, do I want to say that you get the symplectic homology of any of this is going to be 0. Of course, if you Calabi out, so if Filtrations class is 0. So looking at historic manifolds, of course, if it's Floer-theory variety, then this Jacobian is going to be something interesting. So not necessarily 0. So and then we get to the punchline and to this main invariant of today's talk, which is, okay, you do some Floer-theory, you get some construction of symplectic homology, that's great, but what's the outcome of this? Not just being, you can avoid, you can deal with non-trivial manifolds. That's interesting for symplectic topologists, but for anyone else, the question is, okay, what you get out of it? And the answer is, what we get is filtration of homology. So how naturally we get it? Well, see, this symplectic homology here is defined as direct limit. And in this direct limit, if lambda is small, that's what I said on the first slide, for small Hamiltonians, your flow homology is just Morse homology, so just the ordinary homology. As a vector space, as with the ring structure, it's actually quantum homology. So this pair of pairs product, kind of converges to being like a quantum product for a small Hamiltonian. So lambda small. So then the outcome is, in this direct limit, you start with quantum cohomology, and then you go further, and the direct limit you get 0. So what it tells you is that you can get a canonical filtration by looking at, so that's, I'm just repeating, so small slope, it's quantum cohomology, and then in this direct limit, you get to the certain slope. And the question is, okay, what's the kernel of this? Which means I start with a class from quantum cohomology, and then when does it die in the direct limit? When does it vanish? If I know the symplectic homology is 0, such as when it's Calabi out, then I know that every class has to die at some point. And the question is at which point, and that's exactly how do you filter. How do you filter quantum cohomology? So it's like survival time of your class. And I just put this up like generic because you need this lambda to be irrational. So something like, if lambda is 2 or something, everything's a periodic solution, so your homology is not well defined. So you want these lambdas to be like generic, and then that's how you define filtration. So when does my class dies in the direct limit? Okay, so this is just like repeating what I said. So you construct it, you get this Floer-theory filtration by ideals on the quantum homology. The reason why these are ideals is because one can construct a diagram between the quantum product here and the pair of lengths product, and from this diagram you see that this kernel is actually it preserves its ideal. And then if symplectic homology is 0, then this filtration actually exhausts the whole quantum homology. So every class has to vanish at some point. Otherwise, you can just say, okay, well, the infinity filter piece is the whole quantum homology. So that's interesting outcome. So you do some Floer-theory using the C direction, and you get some invariant because it works. Now the question is how. The next 15 minutes, I'm going to say how we can compute this filtration, how much we can compute it, and what do we know about it in general. For now, what you definitely see from the definition is that this is all compatible with cohomological grading. So this filtration makes sense on each cohomological grading as well. So you can restrict to a certain degree. And also what's interesting is that we've seen that this symplectic homology is independent usually. So like in toric varieties, you always get a Jacobian ring, but this filtration actually depends on the C direction. So this filtration really is invariant of not only symplectic manifold, but with C direction as well. So looking at examples, it definitely distinguishes different C directions. So it's sensitive to the choice C direction. And as I mentioned on the very first slide, if you don't like quantum homology, you can just specialize, forget about the nomical parameter and just specialize to the ordinary homology where you get the filtration of the ordinary homology with the cup ideals, because the quantum product is cup product plus the nomical part with the counting D stuff. So that all vanishes. You get filtration by cup ideals. So that's the outcome of this tough construction and all these technicalities and stuff. Now, as I tell you, any invariant coming from Floer-theory is usually hard to compute. But now this coming from C direction, from S1 action, actually we get something done. So there was old work of Ritter, my collaborator, where he proved that in this setup, in the legal setup, now we say this works anywhere. At least what we know is this continuation map, which gives you filtration, right, is known when you look at the slope with integer times. So when you go a couple of times, n times, your continuation map, so coming from the small slope to the slope n, is going to be quantum product by the side element. So again, in symplectic homology, there's a lot of these stuff which so that representation is something which people in algebraic or graph theory is called shift operators. So it's just a story that you have an S1 action by Hamiltonian diffeomorphisms. By counting certain sections of certain bundle, you get this desired element, which is the element in quantum homology. So it's like a Gromit invariant. So what happens is that the continuation maps from the previous slide, which we don't know in general, they're hard to compute, but at least the integer ones are just quantum, doing the quantum cup product with Z element n times. So if you know Z element, then you know the filtration at integer times. Okay, and then that also gives you connection between quantum homology and symplectic homology, because the quantum symplectic homology is directly linked of these doing the quantum product at n times. So it's going to be a localization of quantum homology with respect to the Z element. So if you know Z element, then and QH, you know SH, which is how you get quantum homology, symplectic homology with this story. So then there's proposition which says, okay, in some nice conditions, we know something about Z element. So its non-nomical part is Poincare or Lefsch's dual of this minimum of the moment map. So very like precise element in cohomology, then you get some higher nomical terms, which you never know what they are. If you're found, they don't exist. If you're Calabi-Yau, they exist. So then that already gives us something like A1 resolution, which we see in Nikita's talk. So resolution of A1 singularity, that's example of symplectic resolution. So all this story makes sense, the C direction. So the C direction on the A1 singularity, these coordinates, which Nikita called P, Y, that this is X, Y, Z, right? The simplest C direction there, just act weight 1, lives to the fiber dilation, is CP1. And then there you know this Poincare dual F min is just going to be your zero section, your CP1. So point residual is -2 of that because of the self-intersection. So you get information that your filtration here is going to have two parts. F1, so time 1 you get the H2 class, the class of CP1, and then at F2 you get the whole because so from here you get the F1 is not the whole thing, and it has to be H2 because of the grading reasons, because you're copying with something in the H2. So it has to H2 times H2 is going to be H4, and that doesn't exist for P star CP1. So just grading reasons tells you F1 has to be H2.
What is capital P, capital D?
Oh, that's PD for point residual, which is really less residual because it's
That's what it means for me, but I didn't know which.
yeah. It's just my collaborator likes point. I mean, it's less residual really because it's open, but I guess other people also always put PD. Not okay, so because this being like a locally finite cycle. So okay, this shows that we can compute this filtration for a relatively simple example, because this is topologically simple, just cotangent of CP1. The C direction is also very easy, like you have fixed locus and everything else is one place. But then you're going to go, okay, guess one. There's like 10 more minutes. Yeah, I guess I'll have time. So the other interesting thing is, remember that we had filtration in quantum cohomology, and then we say we can specialize this to the filtration or the ordering cohomology, so something with cup ideals, something which looks kind of down to earth, or at least structurally. And then the interesting thing is, I realized that it's kind of comparable to the Atiyah-Bott filtration, which what is the Atiyah-Bott filtration? It's forget about symplectic topology. You just have like S1 action. Here on manifold, you have fixed locus, then your moment map is Morse-Bott function, so you have gradient flow, and then you just look at just filter your cohomology by this decomposition of by the fixed locus. And how do you filter? You filter by the value of the moment map. So let's say the first filtered piece is going to be the maximum on the moment map, and then you go further away, further to the minimum. So when you capture the minimum, you take the whole cohomology. The minimum is going to give you the unit, or unit is going to be in the minimum block. So that's what the Atiyah-Bott filtration does. And those are going to be actually ideals with respect to topology. So that kind of look very similar to our looking at examples, and then I wanted to see how it compares to our filtration in a very like, simple example, like A2 resolution. So for more general examples, the story gets more complicated, but this is just showing that, okay, let me just first say what we get. So A2 resolution is it's like the next example. A1 resolution is the simplest, A2 is the second simplest. So we resolve the xy minus z3 singularity. And then the score, remember we had the score being like a subvariety, which is all the points which don't leave with this direction. So here, the score is just the central fiber, so the exceptional locus of this resolution. So it's going to be 2 CP1s wedged in point, right? So then let's consider, you can consider many actions here, but let's take this action, which works because x and y has to have the same weight as z3, so that works. For this action, the fixed locus of the core looks like 1 CP1 out of these two and the point of the other one. So this is the picture. These circles are CP1s, so S2s. What the Atiyah-Bott filtration would do is, as I said, so this F alpha here, this point is a maximum moment map, so that's going to be the first filter piece. The F min, the whole CP1 is going to be the second filter piece. So the lower row says, okay, Atiyah-Bott filtration takes this F alpha point and then the whole F min. Whereas what our filtration would do, actually, it also starts with the maximum, but it takes H2 class of the sphere and then H0 class. So it does refine the Atiyah-Bott filtration in this particular example. So it can distinguish between different classes of the same fixed locus, so Atiyah-Bott takes chunks of fixed locus, so it cannot do that. Again, this is like low dimensional example, so in general, the situation becomes more complicated. It's not really clear, whether it's always going to be refinement or not. but it has the same features. Somehow it goes from the higher moment map to the lower moment map within the core, and get ideals by cup product. So it's kind of Floer-theoretic version of it. Okay, then we get to the spectral sequence, which I said is basically the way we compute this filtration for more complicated examples. So before that, we kind of use one lemma, second lemma, third lemma, and so on, but you go to higher dimensions, these are not enough. So what spectral sequence does, and let me just get about the details. So remember in C2D we had a spectral sequence which had the Morse cohomology part and these S1s, the Morse-Bott manifolds of S1 orbits. So that's what happened here. So the first bit of this, so the first blue plus is the Higgs locus, but it's also the same as the ordinary cohomology because of the composition. And then the further, these BP deltas are the manifolds of S1 orbits filtered by the periods. So this TP is going to be some period which can be a rational number. So unlike in C to the n, in C to the n the action was free apart from the origin, so you just get period 1, period 2, period 3, and so on. Already in A1, so for A1 singularity it was the same. For A2 singularity, for example, we've seen here you have some Z2 isotropies from this T squared. So in general, what you're going to get in these columns are also rational period orbits, so like orbits of period 1/2 or 1/3 or something. So you kind of increase the periods all the way to infinity, and that's what's going to converge to SH. So same as in C to the n, if your Calabi-Yau, SH is 0, so then this converging to 0, we kind of know what are the differentials in the spectral sequence. As we've seen in C to the n, we concluded the differentials because we know that it has to converge to 0. But the important outcome, not striking, like this comes from the theory, the important outcome is that this spectral sequence reads the filtration. In other words, filtration is in a filtered level lambda, if and only if the cones by period lambda kill it in the spectral sequence. So like you draw the spectral sequence and look when is my cone gets vanished, by which cone. So the later cones were vanishing the things which are in the later filtered pieces. That's the important and the importance of like this why we wanted to construct this spectral sequence. And then let's go back to A1 resolution, for which we've seen was the filtration, but let's look at the spectral sequence. So this is a very relatively easy example because we said that this action is free apart from the fixed locus, so you just get the manifolds of S1 orbits, which this is O-2 bundles, so the hypersurface is RP3, right? Like in C to the n, we have like hypersurface being S2 and -1. It's hybrid 3, and because for simplicity we do characteristic 0, so RP3 is the same as S3. This is how the picture looks like. So in the first column, you again have the ordinary cohomology, P star CP1, that's just CP1, that's just here. And then in the next columns, you have this period of S1 orbits, which is RP3 characteristic 0, and then the gradient just goes down. So if you draw this, and you know the symplectic cohomology is 0, so everything needs to kind of kill off each other, then you just look at, just play a game, you look at H2 class, well, it has to get vanished by the top of the second column. Look at the H0 class, it gets to vanish by the top of the third column, and so on. And that's it. So from here, you know, okay, well, the F1 is H2 because that one gets killed by the time one column. F2 is that, but also H0 because the H0 got killed by time 2. So that's how you get it from this place. So then let's look at the A2 resolution, which we've seen already. That's going to be our last example. We've seen already one action, but you can play with the action. You can consider different actions. So I think in the example we've seen the third action here, but we can switch X and Y, and we can also look at the first action, which is the induced by the standard C star action in C2, because A2 resolution, A2 singularity is C2 divided by 3. So look at these 3 different actions. They're of course going to give you different fixed locus. So the first action is going to have 3 isolated points. Second and third are going to have this CP1 point. And then And then to get a spectral sequence, we need to know these columns, so that this S1 orbits. How do you get those? Well, of course, you know that one periodic orbit is going to be whole hypersurface. So that's here, like, some length space, S3 divided by Z3. So that's known. But there are these irrational periods here which appear because of the higher weights here, 2 and 3. So where they come from this fixed locus here, they have outward weights. These outward weights, in the first case, are 3 and 3. So we're going to give you, so picture looks like. So we have these two CP1s. And then in the first case, we have these fixed 3 points. So here we have weight 3, and here we have weight 3 complex line. So when you intersect with hypersurface, you get S1 and S1. That's why for the. Did I press? Well, okay. That's what makes me overpressed. Yeah, overpressed. Yeah. Okay, we're there. Right. So that's the first picture. We'll have 2 lines with weight 3, which gives us 2 S1s here for the period 1/3. The second and third case, we're just going to have 1 line each with period 1/2. So altogether, the spectral sequences for these 3 actions. The first action is going to have these 2 S1s happening in period 1/3, and then appearing in period 2/3 because you just rotate 2 times. And then in period 1, you have the whole hypersurface here, and then it just continues. The second and third action, as I said, like you have just 1 S1 in period 1/2, and you have the period 1 length space and so on. So altogether, the spectral sequence effectively tells you what's happening with the filtration. So the first case, you get 1/3 being the H2, and then the whole space, whereas here you get 1 class for each, and that's what we see in this comparison with the table. But now we're seeing it using spectral sequence. And yes, in the end, I wanted to mention something about Higgs bundles, but I guess much time's up. The outcome is that for low-dimensional Higgs bundles, this Floer, let me just figure this out here. So for the low-dimensional Higgs bundles, the Floer filtration recovers the filtration given by multiplicity of the components in the core. Multiplicity is because Kitchen map gives you a scheme structure in the core, like being the inverse of 0. So then this Floer filtration recovers this multiplicity, which is kind of symplectic topology versus algebraic geometry. So I thought it was interesting today. That's for low-dimensional Higgs moduli. Okay. Higher dimension, there's some.
Is a Higgs moduli what? Elliptic curve?
So that's it's all they're like on E1, but with meromorphic points, it's false. Because in dimension 2, there's no, they cannot be the usual Higgs bundle. They have to be parabolic or. Okay, so and for higher dimensions, that's something which we want to compute. So that's open work in progress. Okay, this work for Higgs bundles with 0 is out. Okay, that's all. I'm slightly over time. Thanks for